Third lecture on electric dipole. Today we shall discuss dipole-dipole interaction. Let me first give a certain example, physical example where such things are such thing occurs. By dipole interaction will means two dipoles, one dipole D1, another dipole D2. They are in neighborhood, and there is an interaction, that is the dipole 2 will have some potential energy due to the field produced by 1 and vice versa. Similarly, some force will act on the dipole 2 due to 1 again, and the reverse and the torque. These are the topic of dipole-dipole interaction. Consider a water molecule. A water molecule is composed of two OH bonds, and two OH bonds. It is found that it acts as a dipole of moment P1, and this is another dipole P2, so that the resultant dipole moment is P, which is simply the vector sum of P1, P2. A water molecule is as a whole electrically neutral, but when such a molecule, water molecule, comes in the neighborhood of another water molecule, these two water molecules interact with each other electrostatically. This is the situation. So let me first find out what is the field that the dipole D1 produces at the center of dipole 2. Before going to that, let me explain the picture. This is a dipole D1 with its center O1 having position vector R1 with respect to some suitably chosen origin, and the moment of the dipole is P1. The corresponding quantities for dipole 2 are denoted by suffix 2, and capital R, which is basically R2 vector, R2 minus R1, is the position vector of dipole 2 with respect to dipole 1. First, let me calculate what is the field that is produced at D2 due to at O2 due to D1. Remember that whenever a dipole of moment P is placed in vacuum, the field produced is the This is the field that a dipole of moment P produces at a distance r from the center of the dipole. So, if we want to calculate what is the field that what is the field at the location of dipole 2 due to 1. So this is at, and second suffix is G2. So we write it when the dipoles are placed in vacuum. It is the field of dipole 1. So here it will be P1, P1, and small r will be replaced by capital R. So this is 3 P1 dot R K is as usual the SI factor. So we know that this is field at O2 due to D1. Similarly, if we want to calculate what would be the field at the location of dipole 1 due to 2. So this is the field at this. We can have the expression for E12 by replacing P1 by P2, and you know that this is the position vector of 1 with respect to O2 is minus R. So we can get the expression for E12 from that of E21 by replacing P1 by P2 and vector R by minus R. On interchanging my R by minus R, this scalar part does not change, or the magnitude of the vector does not change. So we write it as 2 minus r, adjust the sign. This is the field. We have obtained the field that one dipole produces at the center of other arm. Now come to the potential energy. We are interested in the potential energy of the dipole 1 in the field of 2, or dipole 1 in the field of 2. So this is the PE of D1 due to D2. We know that whenever a dipole of moment P is placed in an electric field, then if E be the field at the center of the dipole, the potential energy is minus P dot E. This is the expression. So it is the potential energy of dipole 1. So this will be P1, and this field over here is due to dipole 2. So we should write it as E12. So it is E12, that is the field that is produced by dipole 2 at the center of 1, that is this one. You note that there is a minus sign, and if we adjust this sign, this comes out to be this is the expression for the potential energy. Now we have dotted this expression with P1. So this term is there. This becomes P1 dot R. This is there, and this is P1 dot P2. This is P1 by P2. There is a minus sign which has been adjusted. So this term has become positive and this term has become negative. Now if you want to obtain U21, how to get it U21 from this? Why we can obtain starting from U12, we can go to U21. We can go to U21 by interchanging P1 and P2, and then changing R by minus R. This is also valid. We can also come from here to there. So this is the expression. Starting from U12, we can go to U21 or the vice versa. You see that this expression is symmetric about P1, P2. So this process, nothing changes. And changing by R by minus R, the magnitude of the vector R doesn't change. And these two R keeps the thing same. So in other words, this is also U21, that is we call mutual potential energy. When the energy of something which is common to interacting system, one speaks of mutual potential energy, as in the case of gravitation, the force between two gravitationally attracting bodies are equal and opposite, and we say the mutual gravitational force. So this is the expression for the mutual potential energy. So we summarize it as mutual PE for two interacting dipoles is governed by U P1 P2 by R cube minus 3 P1 dot R E2 dot R upon R to the power 5. This is a general expression for the mutual potential energy between two dipoles. Now we shall come to a special case of two coplanar dipoles. That is the dipole moment. If we consider the dipole moment vector P1 and P2, they lie in a single plane. As assume that they lie in the plane of the bone. Then if P1 vector makes an angle theta 1 with the R and this makes an angle theta 2, then the angle between theta y, P1 and P2 is alpha. Note that if this angle be theta 1, this is pi minus theta 1. If this is theta 2, it is theta 2. So if we apply the triangle property of triangle, that is total sum of the internal angles is 2 pi, then we end up with this result. So we can simplify this for a coplanar dipole. So we write U for coplanar dipoles. You see that this becomes P1, P2 cos theta by R cube, and this becomes P1 R, P2 R, cos theta 1, cos theta 2, and 2R cancels the power, and we can take K P1 P2 by R cube common. This part is cos alpha minus 3 cos theta 1 cos theta 2. Again, note that this alpha is theta 1 minus theta 2, so we can further simplify it as K P1 P2 R cube. This equal to theta 1 minus theta 2. So we get from this cos theta 1 cos theta 2, which when combines with this becomes minus 2 cos theta 1 cos theta 2. Another term arises from it is plus sin theta 1 sin theta 2. This is the expression for potential energy, mutual potential energy for two coplanar dipoles. Sometimes problems are given to find out what will be the equilibrium condition for two coplanar dipoles when one dipole is kept fixed and other is allowed to rotate. Then this is the potential energy expression for potential energy. We can find out the torque from it. If we assume that the dipole P1 is fixed and P2 is allowed to rotate, then the torque that acts on it can be obtained by del U del theta 2, and for equilibrium we set it to be 0. And we can get an expression for the equilibrium condition between two interacting dipoles. And special cases may be obtained when the dipoles are parallel. When the two dipole moments are parallel, then alpha is 0, and we can relate theta 1 and theta 2 by this relation. When the dipoles are anti-parallel, that means parallel means the dipoles are like this, and this is parallel, alpha is equal to 0. This is anti-parallel, alpha is pi, and another thing arises, this is 1. This is perpendicular, alpha is pi by 2. We can get the corresponding simplified expression for the potential energy in all these three cases. Now come to the expression for force. For calculating force, we will require these two terms or this term. We are going to calculate the force that acts between two dipoles. Not necessarily they lie in the same plane. So I am just omitting this result, and the result that is going to be presented is perfectly general and is applicable for coplanar as well as non-coplanar dipoles. Now force that acts on dipole 1 due to dipole 2. So let us recall what happens when a dipole of moment P is placed in an electric field. If the electric field happens to be uniform, no net force, translatory force acts on the dipole. If the field happens to be a non-uniform one, and if E be the field at the center of the dipole, then the force that acts on the dipole is this is. One can also give the expression of the force by writing it as the negative of the potential energy. Here we can calculate the field in any two ways, but we shall prefer this one. So we write, this is the force on D1 due to D2. So this is, since the potential energy is mutual, this is same, we write it simply. This nabla 1, that means whenever we place this dipole at the point, this is the coordinate of point R, then nabla represented that I cap del x plus j cap del y, etc. But here the location of the dipole 1 is R1. So the differentiation has to be carried out with respect to R1. We have done this. Now we write it as my, if you use this expression, minus k comes out, and this is nabla 1 P1 dot P2 by R cube minus 3 P1 dot R P2 dot R by R to the power 5. This is the expression for the potential energy. Now let me differentiate it one by one. First, if we assume that the dipoles are fixed dipoles, that is P1, P2 are constant vector, then this operates only on this, and we get the expression like this, minus k common. This is the entire contribution from this term on the assumption that the dipole moments are fixed. Now come to this one. These are the product of three terms. So we have to calculate the gradient of product of three terms. So we use the product rule. So for the first term it is minus 3 P1 dot R P2 dot R nabla 1 operating on R to the power minus 5 minus 3 R to the power minus 5 P2 dot R plus a similar term obtained by interchanging P1, P2. This is the expression for, so let me explain once more. Since the dipole moment are assumed to be fixed, we have used nabla, we have used this expression, gradient of f times g is equal to f times grad g plus g times grad f. And we have assumed that this is constant, so the first term gives a single term. Now here there are gradient of 3 product terms, and so it results 3 terms when the nabla operates on any one and keeping the other two fixed. The first term nabla operates on this, so this is this term. In the second term nabla operates on this term, and finally nabla operates on this. Look at that expression. There are 2 terms. This term and this term, they are similar. So they are of the form calculation of nabla 1 at to the power minus n. They are of this form. Now you know that they are equal to I cap del x1 of operating on at to the power n plus other 2 Cartesian components, which is equal to I cap, for this one I write del at plus other 2 components. Now this term is I cap minus n times r to the power minus n plus 1. My n plus 1, this is the first, and from this we get minus x2 upon x1 by r plus similar terms. You remember that r is r2 minus r1, so this is equal to I cap x2 minus x1 plus other terms. So the magnitude of r is a magnitude of r is r square is equal to x2 minus x1 whole square plus y2 minus y1 whole square, and so on and so forth. So if we differentiate it, is it twice r del x1 is equal to, from this term, twice x2 minus x1 minus 1 when we differentiate it. So 2 gets cancelled, del r del x1 is this by r with a minus sign, that is what we have written. So finally this becomes, this 2 minus makes it plus, so this is I cap n by r to the power n plus 2 x2 minus x1 plus other terms, which altogether the term in the numerator adds up to give you the vector r. So the result is n vector r by r to the power n plus 2. Note that the sign is plus. We generally obtain a negative sign. The sign is plus because of the definition of vector r. So these 2 terms have been evaluated, and let me write these 2 terms first. There will be a 3 term. Here n is 3, so there will be 3 r to the power minus 5 p1 dot p2 times r vector. This is the first term. For this term, there will be 5, n is 5, so this will be 15 minus 15, and the power of r would be r to the power minus 7 p1 dot r p2 dot r times vector r. So this term and this term have been evaluated. We are left with the evaluation of these 2 terms. Here we encounter again a term this time. nabla 1 operating on P1 dot R. So let me calculate this one. Calculation of nabla 1 operating on P1 dot R. This is equal to, for nabla 1 I write I cap del del x1 plus other two Cartesian components, and for this I write P1 x x2 minus x1 plus other two Cartesian components. Here P1 vector has been written as I cap P1x plus j cap P1y plus k cap P1z. So this is the x component. And furthermore, the dipoles are assumed to have constant dipole moment. So P1x, P1y, P1z, they are constants. So when del del x1 operates on this is 0, this part gives you minus 1, and the other two term doesn't contribute. So the result is minus I cap P1x. And when del del y1 operates on the y component, you get minus j cap P1y. And similarly, when del del z1 operates on the z component, this gives you the P1z times the component, it gives you this y is in suffix P1z, so this is minus P1 vector. Similarly, when this is P2, the result is minus P2. So the result is, you see there is a 3 term, so 3 r to the power minus 5 the term will be plus this is the general expression for the force that acts on the dipole 1 due to 2. If you now want to find out what is the force that acts on the dipole 2 due to 1 need to interchange P1, P2, only interchanging P1, P2, this nothing changes here, nothing changes here, and just these two terms get interchanged. One thing more to do, that is to replace vector r by minus vector r. By changing r by minus r, this term becomes negative, this term becomes positive, and there are this term becomes negative, this term becomes negative. So the in together we will have, this is minus F21. That is the force that acts on the dipole. They are equal and opposite. If we decompose the force on dipole 1 into its radial and cross radial component, means force, one part of the force acts in this direction, another part is in this direction. If we assume the dipole to be in the plane, then these two are in radial direction, but P1 have a component P1, this term when multiplied by cos theta gives the radial component, and when multiplied by sin theta gives the cross radial component. It will have a P1 have two components, P1, this is P1, it will be its radial component, and it will have a cross radial component in the negative direction. Similarly, P2 can be resolved into radial and cross radial component, and that will give rise to the radial and cross radial components of the electric field that acts on the two dipoles. It will be interesting to study that the force that the radial component of F12 and F21, they are indeed equal and opposite. See, but the cross radial component and they act along this line, but the cross radial components are slightly displaced, rather they are parallel. Now come to the torque expression. For torque, the expression is already complicated. To keep the things simple, we assume that the field that is produced by one at the location of 2 or 2 at the location of 1 are uniform, although they have highly R dependence and they are not actually constant fields. When a dipole is placed in a electric field, constant electric field, this is the expression for the field. So torque, so we know this. If we cross it by P2, we obtain the torque that acts on dipole 2. Let me work it out in detail. Torque on 1 due to 2. So this is P1 cross E12. And we have an expression. So this is the torque on dipole 1 due to dipole 2. And we know the expression for this. So this we write it as the minus this term. This is the expression for torque. If you want to have an expression for tau 21, we need to replace P vector P1 by P2 and R by minus R. Changing R by minus R, nothing changes, but changing P1, P2, this would no longer lead to minus tau 21. That is the torque that acts on the two interacting dipoles are not exactly opposite. They are not even have the same magnitude, because this here the cos theta 2 sin theta 1 will appear, and in the other case the role of theta 1 theta 2 will also gets interchanged. This is all about dipole interaction. I want to make a fascinating discussion, comparative discussion between the interaction of dipoles and point charges. Let me do it to conclude the discussion on dipole-dipole interaction. Only thing left is the problem set, which has already been given to you. Consider 2 point charges. So there are 2 charges, charge Q1 and Q2, and they are separated by a distance r. In that case, we know that the field that acts on this, a force that acts on it is proportional to Q1, Q2 by epsilon r square, where epsilon is the permittivity of the medium in which they are passed, and the potential energy varies as Q1, Q2 by epsilon r. Now let me consider a system comprising of a point charge and a dipole. A charge and a dipole, charge Q and dipole moment P, they are again separated by a distance r. Then the magnitude of the force is Q P epsilon r cube, and the potential energy is QP epsilon r square. And if we have just what I have done right now, two dipoles of moments P1 and P2, they are again separated by a distance r. Here they are dipole-dipole system. Now the force between dipole is found to be P1 P2 epsilon r to the power 4, and potential energy is P1 P2 epsilon r cubed. Let's note that the change in power of the potential energy as the system changes. This trend continues for other complex structure of electrostatics, that is quadrupole, octupole, similar things continues.